Don't forget to subscribe and ring that bell.
How are you all doing? Welcome back. I just had, 3-4 days off. We had Thanksgiving break. This is the Monday we are returning, Monday, November 28th, 2022. We are going to continue the 2018 practice AP Calculus AV exam that College Board put out 4 years ago. And nice. We get to use a graphing calculator. All right. We're going to start. There are 15 questions in section 1, part B. We are going to do 8 of them in this video. In the next video, we will do 7 of them. I get this question all the time. What graphing calculator do I use? I use the TI-84 plus CE. All right, the CE because I like the color addition. There are so many different actual colors as far as the calculator. Mint green is my favorite. I love it, dang it. I own that one. But there's green, blue, black, pink, gold. I mean, there are a ton of them. Links are all in the comments below if you're interested in grabbing one. They're a little bit pricey, but God, they are so worth it. Okay, let's begin. Graphs and charts and tables, yeah, man. I love them. Number 76 says, the graph of f prime, the derivative of the function f, is shown above from -3 to 3 on the x-axis inclusive. On which intervals is f increasing? All right, well, let's start. That's a nice, easy one to start out with. First of all, I always make sure I know that this is the first derivative, which is the slope of our original function f. That O needs some help this morning. Okay? They want to know on what intervals is f increasing. That means when I have a positive slope. Again, slope is the same thing as first derivative. So anytime my first derivative is positive, keep in mind the y value is the first derivative. Anything above the x-axis is considered positive. Anything below the x-axis is considered negative. How come? Because I have positive y values above the x-axis and negative y values, I mean, you see them right here, are below the x-axis. So we're basically trying to figure out where is the graph of f prime above the x-axis. Well, from -1 all the way to 3. These are all positive values. Okay? From -1 to 3. Ta-da. You know, it's not that I don't like these types of problems. I just prefer to actually do algebra and math, not kind of evaluate a situation. But there seems to be a weakness, especially when it comes to word problems, of evaluating situations. And that's what this question is testing us on. The rate at which water leaks from a tank in gallons per hour is modeled by R. Okay? A differentiable function of the number of hours after the leak is discovered. Which of the following is the best interpretation of R prime of 3? Can't forget that word is. All right, so let's go here. We'll do something red. Okay, so right now, keep in mind, they're trying to fool you with this right here, but R is already a rate, okay, which the water leaks. So if R is a rate of leaking, okay, R prime is the rate, now let's fix that, of the rate leaking. Okay, don't think that this is, oh, it's the first derivative. They kind of give you that first rate or first derivative with R. So this is kind of like considered a second derivative, even though it's the first derivative of R. It's the rate of the rate. If we labeled it, it would be in gallons per hour squared. Because look, it's this number of hours, gallons per hour. That's R. So this has to be gallons per hour squared, or sometimes they write that in gallons per hour per hour. So that's really what I'm looking for. So let's look, I mean, based on the label alone, okay, A is the amount of water in gallons. No, the amount would be to integrate to go back, okay, so that it's not a rate, so that it's just a value, gallons. Can't be that. The amount of change in gallons per hour in the rate at which the water is leaking during 3 hours after the leak is discovered, okay? So change in the rate, that's a possibility, but then look what it says. During the 3 hours after the leak was discovered. This is right at hour 3, okay? During the 3 hours, no. So it can't be B. The rate at which the water leaks from the tank in gallons per hour, 3 hours, no. It's not just the rate, it's the rate of the rate. So it can't be C. That leaves us with a D. And by the way, let's read what D says. It is the rate of change of the rate at which the water leaks from the tank in gallons per hour 3 hours, right at that moment after the leak is discovered. A lot of explanation in that one. A lot of explanation, but I want to make sure you get it. 78. A particle moves along the x-axis. The velocity of the particle at time t is given by v of t, which is 4 over t cubed plus 1. If the position of the particle is x equals 1 when t is 2. Okay, that sounded weird at first. What is the position of the particle when t is 4? All right, so here's what we have. They give us v of t, which is velocity. And then they say position, which is a function x of t. How do I know that? Because the output is 1 when the input is 2. So we have x of 2, well, that equals 1, the output. And then they give us this, too. What is the position? So what is the x at time 4? So when I put a 4 in here, what do I got? Again, this is position. They give us velocity. Oh, my Lord, time again for another one of my little graphics. We have position, people. We have velocity, and we have acceleration. These are always one derivative away. But since I have velocity and I want position, I got to go backward. That's integration. I can integrate velocity to get position. Furthermore, if I have bounds, okay, if I integrate velocity, if I have bounds, A to B we'll call it, that is the position at B minus the position at A. We do have bounds, 2 and 4. Okay, so really this is like x of 4 minus x of 2, which means when I integrate, I'm going to do that from 2 to 4. And this is exactly what I'm going to do to set up to get my answer, because I need to find x of 4. All right? I was about to say we're 2 problems in the calculator section, and we really haven't used the calculator yet. Now we're going to. All right, so let's turn this bad boy on. View attached LCD. Well, I got to put velocity. I got to integrate velocity from 2 to 4. So velocity is still in that black circle in the upper right. And I am going to hit math 9. That's my integral from 2 to 4. Now I've got to put in my function. Alpha y equals enter. I like using fractions when they give me a fraction. So 4 over x cubed, pop off that exponent, plus 1 dx. So this number right here, 0.353 we'll call it. Okay, we'll round that up to the third decimal place. 0.353. That is this part right here. This left side is 0.353. That's going to equal x of 4, which I don't know, minus x of 1, which they give me, or excuse me, x of 2, which is 1. Okay, x of 2, remember, x of 2, I have that, minus 1. now it's just basic algebra. Just add 1 to both sides. We're trying to isolate x of 4. So let's keep that alone. Okay, red. We'll add 1 to this side. Add 1 to this side. Boom. 1.353 equals x of 4. And that's exactly what we're trying to answer, which is choice C. Number 79. The graph, another graph, how lucky am I? The graph of the function f is shown above. Of the following intervals, on which is f continuous but not differentiable? Oh, calculus people, why do you toy with my emotions? Why do you say I can use a calculator but not need one? Continuous but not differentiable. There are only 3, well, there's probably more than 3, but there's 3 major places, situations, I should say, where my graph can be continuous but not differentiable. Okay? A corner, a cusp, or a vertical tangent line. I've got to look for one of those here, and I see one. Oh my goodness gracious. I see one right here. That is a cusp, which means it is continuous but not differentiable. So on the following intervals, these are intervals. They're not coordinates. Don't say, well, that looks like it's at 2.5 and 2.5. No. They're not asking you, these aren't coordinates, they're intervals. So when x is 0 to when x is 1, no, what happens between when x is 2 and 3, which is choice C. Hello, bing bong. This one looks like it's going to be a little bit of work, but let's check it out. The first derivative of the function f is defined by f prime of x, which equals x squared plus 1 sine of 3x minus 1 for the given x values or interval between negative 1.5 and 1.5, not inclusive, meaning it doesn't include them, okay? They're not equal to, it's just less than. On which of the following intervals is the graph concave up? Oh, people. Concavity is second derivative. If it's concave up, that means the second derivative needs to be positive. Second derivative is the slope of first derivative. Okay, same thing. I want to see where that is positive. So I'm going to look at my graph. I'm probably going to have to do like min-max. I'm going to have to get coordinates and figure out where the slope of my first derivative is positive. So I'm going to graph this. This is my first derivative. Okay. Bang, bang, do, 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 da, dee. Put this right here. Turn this on. And clear this out. Go to y equals. Make sure you're in radians. Okay. Which I am. You just hit mode. And see right there, radians is highlighted in black. If this was highlighted in black, that would be degrees. I have a class set of calculators, and calculus uses them, but so does algebra 2. Algebra 2 should be in degrees most of the time, so I always tell my calc students to check them. Okay, so let's go back here. And we have, in parentheses, x squared plus 1, parentheses, sine of 3x minus 1. Remember what our interval was? To the left of that red box, it goes from negative 1.5 to 1.5 on my x-axis. So I'm going to go right to my window, and I'm going to make that negative 1.5 as my minimum on the x, and 1.5 is my maximum. I don't know if I got to go from negative 10 to 10 on the y, but let's take a look. Now, I don't care about anything outside going left and right. Anything that's more left than negative 1.5. Like right here is negative 1.5. And right here is positive 1.5. I don't care about anything else because this right here, I don't care about anything else. So I guess what I'm going to have to do, I guess I know. Okay, it looks like it's a positive slope. I'll do this in green. No, man. Positive slope here. So I got to figure out what this point is, because here's a positive slope, but then it's negative here until it hits this bottom. And from here to here, it looks like it's positive again. Okay, so I really don't care about this in between. I just want to know what coordinate is here, here, and here, so I can state my intervals. Because, man, I can't change the ink. I can. Look at me go. Oh, man, no, we're not doing that. Let's go back to green. Because I have a positive slope in this section. And I have positive slope in this section. Remember, where the first derivative is positive, the slope of the first derivative is positive. That means the second derivative is positive, and that's what we're trying to find. So I'm going to go to second trace, because that's calc, and I'm going to calculate a max point. Oh, I should have started with that minimum. My little spider dude was so close. I'm going to go all the way over here. Right there. Enter, there's my left side. Go over here. Enter, there's my right side. So this x value is negative 1.227. I'm going to put this right here just for the sake of keeping it. We're probably going to need these values in a moment. Now I want to find this minimum point here. So I've got to do this all over again. Second trace, minimum this time. And I'm going to bow tie myself, or create bounds, bookends, if you will, on the left, on the right, and hit enter. That x value is negative 0.24. Let's bring this out here. This will probably come in handy as well. Line these all up. So nice when you could, what you can do with technology. And we have one more. Oh my God. There it is. Don't get that. Don't have that go away. I'm recording. And now we need to find this maximum. So second trace maximum. Right there. That's good. That's the left side of it. This is the right side of it. Hit enter. Okay, 0.96 is that x value. So I'm going to go here. And it looks like, and when I say it looks like, I mean it is. All right. This little wedge part right here that's positive goes from negative 1.5, this is where I start, to this value right here, this x value here, which is negative 1.22. So this little positive jut goes from this on the x-axis to this on the x-axis. So negative 1.5 to negative 1.227. Okay, on the intervals, negative 1.5. Why am I not seeing that? Am I losing my mind? Am I out of my mind this time? Which of the following intervals is the graph concave up? Oh, that's not at the max point. Look what happens. See where this is? That's left of this. It should be right here. It should be a little bit left. Woohoo! That should be a little bit more negative. Wow. I moved my little, okay, let's go second, trace, maximum. Let's make sure there for a second. Oh my goodness, look at all the way he is. I don't know if I can go this whole time, but I'll try. Right there. Hit enter. Hit enter and enter one more time. Now, wow, I must have moved. That was weird. Negative 1.34. I'm going to have to go back and watch that video and see what happens. So we'll put this right here. Wow. Good catch. So from this point, which is negative 1.5, to this point, which is negative 1.34. Okay, that's where I have a positive, which is right here. That's the only one. I mean, that's our answer. Well, let's take a look. Also, from this point to this point, okay, this x value is a negative 0.24, and this x value, which is right here, is 0.96. Right there. Choice A. Woo! Wow, look at us. I don't know what it is, but I like these types of problems. It's not a lot of work on our behalf because it's a calculator one, but I just like taking integrals and derivatives. Yeah, I know, I'm a math nerd. 81. During a rainfall, the depth of water in a rain gauge increases at a rate modeled by R of t. Keep in mind that R of t, once again, is a rate. All right? Where t is in time and hours since the start of the rainfall, and R of t is measured in centimeters per hour. How much did the depth of the water in the rain gauge increase from 0 to 3? All right. Well, let me write this. I have F, I have F prime, and I have F double prime. This is one derivative away. This is one derivative away. And backwards, well, those are integrations, right? On the previous problem, we had position can be for F, velocity can be for F prime, and acceleration is F double prime. That also happens with rates. If we have a rate, which is centimeters per hour, this is centimeters per hour. Second derivative is centimeters per hour squared, or in case of a previous problem we did, centimeters per hour. Remember, you can write hour twice, which means the original function is just centimeters, so I'm going backward. All right? So again, derivative is this way. Okay, integration is moving back. Right now, they gave us this, centimeters per hour. That's what R is, and that's what they give us. They want to know how much did the depth of the water change. Depth is just measured in centimeters. That is not measured. How deep is that? Centimeters per hour deep? No, it's just centimeters deep. Okay, so I'm going to have to integrate this to go backward to get that. So I'm going to integrate whatever my R of t is, dt, don't forget that dummy variable, and I want to integrate it from a time 0 to time 3. I'm literally going to put that in a calculator, and this right here is going in for R of t. Let's go here. Second quit. Go math 9 from 0 to 3. We are going to put in, move this down a little bit so we can see, 0.5 plus x, because we use x in the calculator. Cosine, make sure you're in radians. Oh, they have a fraction, so I am going to use the fraction function. That is pi x cubed. Pop off that exponent, come down to the denominator, over 80. Now, I have two opening parentheses. I need two closing parentheses, so I need one more. Now they match, dx. Okay, what I mean is, well, let's get rid of all this junk from the previous problem. If I have two opening parentheses, I need to match that with two closing parentheses, okay? 5.4, even if we round it 3 decimal places, well, I guess it'll be 401. Dagnabbit, 5.40. This will turn to a 1 because the number after it's 5 or bigger. Yeah, see? It's D, see? It's D. C is in S-E-E, C, visually, not C as in the letter. Not to confuse you with the wrong answer. It's choice D. 82, 2 more problems. We are moving along really, really well. I haven't used one of the fancy colors. I mean, I used gray. Let's go with this nice orange, nice burnt orange. It's still November. We have a few more days till December. Then I'll go light blue. 82 says, let f be a function such that f of 1 is -2, and f of 5 is 7, which of the following conditions ensures that f of c equals 0? This is some x value in here. I don't know it yet. And that means the y value would be here. It would have to touch the x-axis. Anytime the y-coordinate is 0, that point is on the x-axis. For some value of c in the open interval from 1 to 5. All right, let's just do a little sketch here. Here's 1, and here's 5. Because they give me an x value of 1, I have a y value of -2. This point right here. And when x is 5, I have a y value of 7. We'll go right up here. So they're saying there has to be some value c in this interval from 1 to 5. C. There's some value here that has to have a y value of 0. Which means what I should do, yeah, let's do this. Move that away for a second. Go here, go here. That means there's some value c that has the coordinate right there. I want to put the dot with it. So somewhere along the line. Now, you may be saying to yourself, come on, there you go. You may be saying to yourself, well, okay, it doesn't matter where it is. No, it's all apart. In order to get from here to here and touch the x-axis somewhere, it has to be continuous. It has to be a straight line because I cannot get from -2 all the way up to 7 without crossing the x-axis as long as my function is continuous on that closed interval. Boom. All right. And there you go. That's a basic, I think, a common sense one as far as calculus is concerned. But I digress. Let's do the last problem. And we are going to end today with a calculator problem. How do I know? I'm looking at B, C, and D, the responses. You are not going to get that with your own little brain and paper and pencil without the use of a calculator. But, you know, who knows? Maybe you can. That would be impressive. 83 says, the acceleration of a particle moving along the x-axis is given by a of t equals t minus 8 sine of t for t values between 0 and 8 inclusive, meaning it can be 0 or bigger, it can be 8 or smaller, inclusive. At what value of t is the particle's velocity decreasing most rapidly? Okay, velocity decreasing tells me that velocity is changing. Velocity decreasing is a change in velocity, which would be the most change, like negative. The most negative, I guess. A change in velocity or a rate of velocity is acceleration. So I got to figure out when acceleration is the most negative value. Velocity is decreasing. The smallest or lowest acceleration point. The biggest negative, so to speak. All right, so again, I'm going to go to my handy-dandy calculator. The TI-84 Plus CE links are in the comments below. I have the mint green one. I've said that all the time. I love it. It's the best. Let's get rid of these. Turn this on. Now let's clear that out, even though oh, that's a graph. Let's go here. Let's clear this out. And let's put in our acceleration function. We have x minus 8 sine of x. Again, we're using x instead of t. And my x-axis, I only care from 0 to 8, that interval they gave us. So I'm going to go to my window. I'm going to make it from 0 to 8. And let's graph this bad boy. Boom. Now keep in mind, this is acceleration. The y value is acceleration. We graphed acceleration. That means any y value is acceleration. So if y is positives up here, that means I have a positive acceleration. If y is 0 on the x-axis, that means acceleration is 0 when it touches the x-axis. These values down here that have a negative y, That tells me where my acceleration is negative. Acceleration is the change in velocity. It is the change in velocity. So if I want to figure out when my change in velocity is the most negative, I figure out when my acceleration is the most negative. And that seems to be, I don't know what this negative value is right here. I mean, I don't know if it's exactly right on the whole number or not. I don't care. They just want to know when. My x-axis is time. So I want to know the x value for this min point right here. That's all we got to do. So I'm going to go second, calculate, and I want to get a minimum value. I want to locate the minimum. Oh, my Lord. A lot of beat about us this video. Beat about left, right here. Going to go to right there. Hit enter one more time. And right at this point, it's 1.419 or 0.420. And my actual y value is negative 6.505. Remember, I want the time. They're asking me when. So I want the x value. 1.420 if I round that. Okay? That looks like choice B. There you go. That was a nice, simple, 31 minutes. Not too long, not too short. It's good for calculated problems. I will see you next time when we finish the next 7 problems of the 15, because we just did 8. Look at math. It's always useful, kids. I'll see you then.
Don't forget to subscribe and ring that bell.